Thank you. Can everyone hear me? There's this knob here that I can turn up to be louder, which is quite exciting. So we'll see how it goes. It's so wonderful having just both the large amount of applications for the Spotlight talks as well as the interest in computer vision, because it's both one of probably the areas of deep learning architectures and machine learning that has received a lot of attention, but it's also the area that has these very interesting and nuanced questions of what next. And in some ways, parts of computer vision are incredibly underserved. So I'm hoping that a large objective of today is to explore with all of you some of our thoughts and the speaker's thoughts on what is the frontier of computer vision and what are active open research questions. To that end, a lot of what I hope to do today is to set us up in thinking about where have we come from. And so the first talk is really what has brought us to this exciting moment in the history of computer vision, but also what are open questions. And here I'll caveat, I'll say this will probably over-focus on perhaps questions I've been thinking about a lot. But also I'm hoping to preserve some mystery for some of the spotlight talks and the panel, who will also discuss certain areas. And the main objective that I hope to get across is just how nuanced some of these questions are, and how even in areas that we consider solved, in fact, like perhaps only one dimension of the problem is solved. So to briefly kind of echo what Daniela kindly introduced, I do research at Google Brain. My area of research is interpretability in computer vision models, but I'm also very interested in model compression. So particularly for convolutional neural networks, how can we take these huge networks and make them much more compact as a representation, which is particularly important for resource-constrained environments. And I want to start by bringing up a really interesting piece of history. So in 1940, at the Dartmouth conference, that was the first time that a group of researchers came together and really talked about this idea of we want to impart human skills and human ways of thinking about the world into machines. But in 1966, there was a definite effort to focus on computer vision tasks. And that effort was essentially two researchers saying, oh, this would be a really fun summer project for some undergraduates. And so the stated objective of the summer was to essentially create ways to identify patterns in images and successfully classify them. It was perhaps a heavy burden, but it was the start of a larger trajectory, which is how can we extract information from images in meaningful ways. And this actually involves various different tasks. So perhaps the one that we're most comfortable and think about is image classification, because that's been the subject of a lot of attention. But there's also object localization, object recognition, so object detection. And this is much harder, maybe because essentially you're adding additional constraints on how you want to extract information. And so object localization, you're not just trying to identify the class, you're also trying to predict the part of the image where the class is present. And then object recognition, you're trying to not just classify one object, you're trying to classify all the objects in the image. And so it's useful to start with thinking about progress on image classification, because this is, I believe many of my colleagues will say, this is practically solved. And so it's fun thinking about how we got to a plateau of kinds where there's a consensus of there's being breakthroughs. So image classification is really this idea that you want to, it's often treated as a supervised learning problem, and you're just trying to correctly return the class, the main object present in the image. And image classification was thought of as a very difficult task because of two properties. One is that it's very high dimensional data, which is often very correlated with complexity. complexity. And then second is that we are just very exceptional at this task. So to be on par with human level performance was considered difficult. And humans are good at this task because essentially we're very good at variations in images. So we're very good at seeing an image in slightly different lights or angles and still being able to accurately classify. We're also extremely good at recognizing faces. We have the ability to recognize faces and store an incredible amount of different faces. And really what I'm talking about with the first point is this ability to generalize, that you may have slightly different samples of the same object and you're still able to accurately return the correct prediction. And the high dimensionality is really because digital images are essentially like a painful amount of features. So like if you have a digital image, you have one input that is associated, in the case of like conventional scaling for ImageNet, for example, with like 250,000 data points, which means that like a large objective of how we want to approach this task, at least initially, is to arrive at a more compact representation that's still informative. And then we can apply some type of final classification layer too. And the second point I kind of touched on a bit, oh yeah, I did touch on it. Lovely, I've said all these points. But this is fun. I was teaching at Data Science Africa in Kenya, and we did a fun game where we were trying to, I posed it as a question. I use photos of myself. It's kind of awkward. I don't like when people take photos of the slides. It sounds like I'm just an egomaniac. But but this is like essentially, I just wanted to, it was easy to use my photos because of privacy, but I wanted to get at the point that like, I'm curious what other people think. So let's say that I'm just trying to classify myself, and I just train on these data points. What images would I struggle classifying here? What would the model struggle? What do people think?
7.
So someone said 3, someone said 6, 1. Yeah, and what are the properties? So what's 3 got going on? Pardon? Multiple people. Yeah, excellent. Pardon? Lighting? Light? Oh, the lighting. Excellent. Yes. So perhaps there's different tones in 3. Far away. Someone said far away. Small. Yeah. Small. Yeah. It's so small. Yeah. Basically at the other side of this building. Yeah. And what about 1? Lighting, right? Yeah. And I'm guessing 6 is somewhat similar. What else? Is there anyone that you think an additional data point that we struggle with?
7.
Yeah, 7. What the hell am I doing there? Yeah. Yeah, what's wrong with 7? Go ahead.
I've got a question about 7. So it seems to me that you're wearing the same clothing, or at least the same shirt in 7 as you are in one of the training set images. So there's at least one kind of feature that's present in both the training set and that example in the test set. So I'm wondering whether we'd actually be able to classify that easily.
Yeah, that's fascinating. No one's said that before, and that's also a suggestion I should change my wardrobe a little. But interesting, yeah, that's actually a very good point, because actually what you're getting at is probably broadly termed data leakage. Perhaps there's other things that are not my face or not my intrinsic characteristics that can be leveraged by the model. Often data leakage is thought of as a problem, essentially that you're relying on background data that may impede generalization, but it can also be fair because humans do this a lot. Like we will often pick up on cues that are not the direct object to arrive at a classification. Kind of like dogs are often photographed on grass, and so a colleague of mine, perhaps this is an interesting tangent for some of you, but a colleague of mine did an experiment where he was doing adversarial examples for humans. So we would flicker animals and photos, and you would have to say dog, cat. And his anecdotal qualitative observations after the experiment was that humans would rely on the green flash to say dog, because we're just used to seeing dogs outside, which was interesting. But yes, I love that point. That's so excellent. excellent. So 7, what else about it might be tricky if we go to Western? Go ahead, sir.
Yeah, the pose.
The pose, yes, yeah. So the pose is very different. Yeah. What else? I'm not really showing my face. So in these photos, there may be angles, but at least my face is visible. So this is interesting, and this is actually like you were very well calibrated with the previous group of students I did this with, so it's excellent, although that was novel, so I love that. But this is why it's so tricky. There's like the challenges of computer vision are really, and even for image classification, are how do we generalize? Like if we have things like viewpoint, scale, illumination, but other things like occlusion, if you can start to understand the complexity of the task. And so how this was initially approached as a problem was essentially that there were 2 separate steps. So you have an encoder, which is essentially the goal is to extract a useful representation that's more compact. And then you have a final layer, which is your classification layer. And really the goal of the encoder is to map things to a low dimension. And some of the examples of this can be fairly simple. Like you can just translate your image into a histogram of pixels and then try and apply a linear model at the end. But there's some that were actually very, very good for specific tasks. So back to visual words is one, but also histogram-oriented gradients. And often there were like multiple steps applied. And then at the end, an SEM was the final layer. And as I said, like some of these were excellent feature extractors that were human engineered. And they were very good for narrow tasks. But where they struggled was when you try and generalize beyond. And often the other, I guess, painful part of this is that you were essentially doing various independent training steps. And so that always adds a bit of noise to your approach. And so the entry of the CNNs was really, the contribution was the single differentiable function and an end-to-end classification pipeline. And once this was introduced successfully in 2012 and performed well on the ImageNet Classification Challenge, the consensus was that there was no going back. It so outperformed the rest of the submissions that everyone switched over to CNNs. And so the big gain, as it was measured in that competition, was accuracy. And in fact, like a lot of the early conversation around what is a good representation, what's the quality of the representation, is accuracy. In fact, still, a lot of research gravitates towards demonstrating improvements in accuracy. But I would suggest that, here's a key takeaway. Perhaps a well-known one. But I would suggest that this raises the question of a finish line. And this raises the question of where are we now? And I think one of the things is that the key development in research since 2012 has been the introduction of a huge amount of research attention on dimensions or properties of computer vision models that appear not to be captured by accuracy. And this is fascinating. And this really gets to like the core of us trying to understand what are essentially the properties of the function that we've trained, that we've learned. Because by delegating representation to the model itself, we also delegate the ability to be able to articulate what the function is in any type of compact way. And an example of this is, well, this is the area that I've been doing research on, which is interpretability. And there's like a huge flurry of attention saying, what the hell, like, what we need to know what these models are doing. But it goes beyond that. And so there's various different subfields that have emerged, mainly because trying to understand the relationship between accuracy of the function learned and other desirable properties that we may want to embed within the function. Example of this is model compression. Like, how easy is our function to evaluate at inference time? How easy is it to store? Because what we've noticed is that we essentially keep on scaling the amount of parameters in order to gain more accuracy. But there's reasons why we want to constrain this. Interpretability is an example that I've done work in, but there's also this idea of vulnerabilities in the model. So if we can purposefully modify inputs to incite undesirable behavior, or do anything else that is not controlled by the model itself to essentially create an undesirable outcome, this is both the field of a lot of research, but also the field of perhaps some fairly gloomy outlooks. Most people who are working on adversarial examples tend to be reluctant to say there's a silver lining right now. And that really gets to the nature of these models, which are essentially, if you have a differentiable function, there's always going to be some way that you can update the input to move it across the decision boundary. The question is, how big does that update have to be? And right now, the consensus is it doesn't have to be very big. And you can do it with very little computational cost. And then there's fairness, which is really like this idea that the way that our models are trained and the decisions that the models arrive at should reflect the beliefs that we as a society have about how they should be served to their communities. As there are examples I mentioned, there's actually maybe I'll do a quick tangent here because perhaps there's already quite a bit of familiarity with adversarial examples. But there's actually a work by a colleague that proposes that the current framework is entirely wrong for thinking about adversarial examples. It's Justin Gilmer just released a paper, I believe, with a co-author. It's worth looking up because what he says is that perhaps the way that we structured it is inadequate in two directions. One direction is that if we wanted this to be the framework, this is the reason why this framework of perturbations has been chosen is that there was initially consensus that it was a useful framework to discuss vulnerabilities while being narrow enough in scope that it could be a good exchange of research. And now there's this thought that, why do we're not doing very successful at progressing on this task given this framework. Either we should move to more realistic attacks, which is what you would find in the real world, where he has some cartoons in the paper, which is actually very atypical of a research paper. But one of the cartoons is basically, he's like, why do we even need to perturb the input of this model? We can just remove the stop sign entirely. It's fun, but he's getting at we may have a contrived language to talk about this problem, and either we loosen it and talk about more realistic issues, or we should make it even more narrow so we can actually try and make progress on it. So that's fun. Interpretability is the subject of most of my research, and here what we're trying to ask is these computer vision models often are deployed in very sensitive domains, and we must, in some ways, where there's an intolerable human cost for an incorrect decision, there's almost an accountability that we should be able to explain how the convolutional neural network arrived at that decision. Those sensitive domains include things like self-driving cars, or healthcare, or credit scoring. I do want to do a tangent and talk a little bit here, because this is not a computer vision model, but I think it's really interesting because often the subject of my research is it's often perceived as a police task force, where we're trying to identify what went wrong. But I think interpretability is actually this much broader effort to understand where the model function diverges from human performance. And I was in San Francisco, and I was going to the OpenAI Dota Challenge, and that was really fascinating. Because not many people would describe it like this, but that was an interpretability exercise. Because they basically beat the human players. This was before the universal challenge, where it was the other way around. But in the practice runs, they beat the human players round after round after round. But people were still interested. It wasn't as if it was a boring match. People became interested after the first two losses in understanding what are they doing differently, what are the bots doing that humans are not doing. And understanding that divergence can often be viewed as positive thing. How can we as humans learn from how a very different function is approaching the same task, which is fascinating. But even here, we're not. I would say it's early stages of research, and mainly because I'd say not through a lack of research attention, but mainly because a lot of the effort that I sense is very promising is to finding how to measure progress on the task. So as many of you, this will ring true, like for any task in the scientific field, we want some way to measure progress. The interpretability, it's hard to know if we've reached the finish line. It's hard to say, okay, this is interpretable, good to go. And so a lot of how, what I've been doing in my research is trying to understand, can we articulate desirable properties formally, and then given that, create evaluation frameworks. But here's some current approaches. So one is model distillation, this idea that you'll essentially distill the knowledge of a more complex model into one that's sort of is more inherently interpretable. The other is interpreting the role and importance of certain building blocks. So the images are from Priscilla's blog, and essentially like that means we have a house, which is the model, and we're trying to understand what certain pillars do. And so you look at like a specific neuron and you try to understand, given that, or perhaps given a neuron and specific input, what's the role of that neuron? And then there's also these methods of trying to estimate the importance of a given input. So here, if you have a given input, this is a very simple gradient heat map. So it's saying, given this input and given a layer of the network, what's the gradient of that logit with respect to the input? And so you get these heat maps of what the model attaches more, what contributes most to a given neuron. These are interesting at being the subject of some reliability studies. I guess I should perhaps caveat interesting what I mean there. By interesting, I mean like these are very widely used. This is one of the most commonly used interpretability tools. This is also the method that's particularly for healthcare, where doctors have to look at every example. It's been the subject of a lot of attention as one of the most promising ways to deliver interpretability for medical tools. However, there's very interesting research questions here of actually, are these heat maps, which humans may find meaningful, are they also reliable reflections of the network? There's also tools that require the human direct the area of investigation. I think it's very interesting, because often we think of interpretability as an answer. Tell me how to make this decision. But in fact, like a lot of data work is an exploration. So this is like TCAT's a perfect example. So I want to briefly talk about another area which I think is very interesting in computer vision. And I mainly think it's very interesting because a lot of solutions to problems depend upon our ability to succeed at placing resource constraints or embedding certain desirable properties like model compression into how we train architectures. And so what do I mean by model compression? I mean, there's been like this remarkable growth. Actually, it's most striking when you see Lynette. I don't know if Lynette's on this chart. No, not even on this chart. So like the earliest models were just, compared to the amount of parameters in models today, it's kind of a joke. It's like, it's this absurd surge in the number of parameters. And essentially that's just very correlated with the number of layers in a network. And why is this, I mean, why is this trajectory happening? Maybe someone can throw it out there. Courage. Courage. Yeah, go ahead. Pardon? Yes. One is we just have this, you know, we can do it. But I mean, there must be an interest there, right? Pardon? Oh, the question, excellent. The question is, why are we both adding more parameters to these models as well as perhaps, I mean, at times amounts to the same thing, making them deeper. And so one of the points raised, which was excellent, was that, well, we can, why not? Yeah. Why? Gas is cheap, let's do it. Yeah? Go. Sorry, go ahead.
So the question is, why do you want to add more gas?
Yes.
think we believe that deeper the layers, the better the application's performance.
Yes, yes. So that's exactly it. There appears to be this relationship between accuracy and the amount of parameters in the model. This is very interesting, by the way, because some very interesting research has already shown that with a single hidden layer, you have a universal approximatable function. And so there's a very interesting question as to why this is the case, that we need to start training with so many parameters in order to arrive at a convergence pattern that leads to a desired level of accuracy. For example, like this is there's some really compelling papers that come out and everyone's like, whoa, that's such a cool set of empirical experiments. So this is one of them. The other one I always think of is the randomized inputs experiments. And I'll briefly talk about both tabs. But this one is essentially, what it found was, it found that it could use a few parameters from each feature, from each filter, and then just predict the rest. And so it could predict up to 98% of all the weights in the network. And it shows this for fairly large state-of-the-art networks. What does that tell us? Like, what's the takeaway then? We don't need it! Bravo, the gentleman in the third row. Like, well, it at least suggests that we should be thinking about justifying why we need it. Because if all these parameters are so correlated, and in fact we can remove a lot of them without significantly improving performance, it raises the question of why they're needed. And the other paper, which is quite fun, on a slightly different vein, is this, and I raise this because I also think this is a nice time aside to suggest the importance of empirical work sometimes. There's importance for both theory and empirical work, but particularly because we do now have more compute, a lot of really interesting results come out of. Go ahead, question in the back.
One question. Well, isn't redundancy,
or a statement, go for it.
Isn't redundancy good for robustness?
So, isn't redundancy good for robustness? So robustness, I'm assuming that you mean generalization properties. So that as well is not, so perhaps I'll put it this way. A lot of compression techniques essentially remove a lot of parameters, a lot of weights, and still have fairly impacted robustness as measured by tested accuracy. There's interesting open areas of research as to why, because perhaps like one thought is, and this is always interesting to talk to Mr. Fadlak, he's quite interested in this area of research. One thing is that perhaps the model just learns calming passes anyways, prototypes, and like the critics, it hasn't ever learned well. And so you can still get away with removing a lot and it still won't impact the tested accuracy. If you follow that to the natural implications at the end of the argument, it's a slightly gloomy picture because it suggests that to some degree your model was never that great anyways. But the degree matters, and I think there's been very little research that trying to articulate the degree. So yeah, but excellent question. That was really good. And so this is a very exciting area and undisturbed area of research, which is, can we, oh, go ahead.
Sorry, I was gonna ask, I was reading the abstract of that paper.
Oh, from there, wow, yeah, actually it's really good. I guess it's, yeah, it's zoomed out. I couldn't do that.
Yeah. So I could see that the paper says that in the base case scenario, 95% of the weights can be predicted. Do you know what the worst case is?
I think they show bounds, but I mean, the reason this was so compelling is that it wasn't a large range. Yeah, but yeah, I would look it up. I don't think it's, yeah, if someone has a Wi-Fi, look it up and at some point by the end we can confirm. Can we train more compact representations of with comparable accuracy? So the reason I decided to spotlight this a little is that later today you're going to hear about a lot of different areas of computer vision. And on the panel, you're going to hear from researchers who are working in entirely different fields in image classification. And for good reason. I think it's very important to know that those are even more difficult. But I decided to dedicate some time to this in this talk because this is in some ways one of the barriers that I think will become the most tangible to researchers in actually taking the breakthrough and applying them to the benefit of problems. The promise of this problem is that tiny computers are everywhere. So the most smart devices have compute associated. The issue is in the gap between the current requirements of training and inference and the models themselves and being able to leverage that compute. This is, I centered on this and I really enjoy this fact because it's a fun aside as well, but the growth of mobile phones in Africa is stunning. It's absurd. Oh yeah, I always have this. Is this right? Yeah. Okay, so the fact is that now, 2016, probably there's more than one cell phone per person. Does this sound right? Oh, you're nodding. Okay, excellent, excellent. Any contrarians? Everyone's like, no, we agree. Great, I have. So actually, it's not quite right because, what this does is the reason I bring this up is that it captures another dynamic fact about the use of cell phones, which is that mobile penetration is about 50%. That's the estimate, but many people have multiple SIM cards. Because essentially they leverage multiple telecoms and switch out and switch in depending on the rates. So again, it's just I think this is really interesting because that highlights just the depth and essentially the richness of using and deploying machine learning to. Oh, we have a question. Wow, and we had a colleague direct the question. That was excellent coordination. Go ahead. Yes, that's the next point. So actually, that was a perfect segue. So few of these are smartphones. It's a fraction. And why is that a problem? Yes. So not only is it constrained by most phones are pre-smartphone, but also even if you think about smartphones, the hardware requirements tend to vary considerably. So it's actually not just a machine learning problem; it's a hardware problem. Because I do want to communicate this point because it's one of the most underserved areas, which is that traditionally hardware is developed siloed from machine learning. And so, in fact, the NVIDIA is a perfect example of that. It's for gaming. And so then researchers came along and were like, whoa, this is amazing. But it's rarely been a symbiotic relationship. And the fact that one has really informed the other. But now with the presumed end of Moore's law, which is that you can pack a lot more compute on smaller and smaller chips, essentially the constraints that researchers have are perhaps both more binding as well as essentially to take these innovations that we've made with models like Inception and ResNet, we have to think more carefully about how it interacts with hardware. A great example of this is that currently on a TPU, which is the Google hardware, there's certain operations which a TPU is extremely good at and is being designed for. But this, in effect, also affects what models researchers like. So there's this odd relationship there, right? Why can that be interesting, or at least, why would I use the word interesting there? Who has a thought? Go for it, bravo.
If researchers are only interested in the latest technology and are driven towards developing models that will run at their best on TPUs, what they're doing won't be that applicable for less constrained hardware.
There's that layer, absolutely. That gets to the 2 points raised by the lady in front and the lady in the second class row, which is that there's this really gap in constraint with research. We don't feel or experience research constraint, and so your suggestion is perhaps it just won't influence how we think about the problem. Yeah, there's another layer here, which is, go ahead.
Well, I think scientific breakthroughs come from constraints. If you have unlimited money, unlimited time, you don't even know what to do. But if you say when you got this amount of money, this amount of space, this amount of whatever, then that's where you get really creative when you actually get better speed.
Yeah, so I completely agree. I'll call this opinion section, but this is my personal sense of like how research, the very exciting research directions come out of constraints. And I sense like there's another layer here, which is not quite about even immersing yourself in the research problem. It's more that if there's this relationship between hardware and models, perhaps like some of our models that are good are actually not seen to be good using things like accuracy on this hardware. So I'll just leave that thought. But like essentially, like if the model is not optimized for the hardware, it may still be very good for computer vision, and it maybe is still a very novel way of doing this task. But we almost have a bias there, right? And so I think it's interesting to think about that. And the more that hardware developers and machine learning researchers talk, the more you can get to a more realistic perspective on, even for smartphones, how do we think about this? Because right now, for smartphones, it's a fairly constrained picture. Go ahead.
So is Snapshot a good example of that, where it's technically better performant, but it's slower to train?
So are you talking about Hinton's capsules?
Yes.
So excellent. You know, I really want to do a foray into the capsules, but then we have a wonderful spotlight talk, which is just about capsules. But yes, exactly. That's precisely what I'm trying to get at, is that, you know, we've settled on essentially convolutional neural networks as one way of doing this task. The same way that our human eyesight is one way of doing this task. Capsules, I think, is Hinton's quite grumpy assertion that we must not settle, because this is like this was advances made in 2012. We're in 2018, so we can't just say it's a rainy day and cuddle up by the fireplace. So I want to do a quick check. Danielle, how many days of time? Okay, excellent. That's all I need. Okay. Yeah, perfect. So I'm going into the so where are we moment. So go ahead.
I have a point on that actually. So how much do you think that getting the models to work in a resource constrained environment is an engineering problem versus a research problem?
Yeah, so I have framed it as an engineering problem in this context, because what I've said, I've essentially motivated it as saying to solve all these problems we need to do it. But I would suggest that I did that partly trying to gauge the interest of the audience. It's in fact also both a very important theoretical problem, because the question is still out as to why we need such large models. And it's an important, it's not only important to try and justify why we need it, it also gets to fundamental theory about, I'll mention like a specific paper that recently came out that was quite interesting, that was trying to suggest that perhaps, and I'll just say that it inspired this vein of paper, which is that it's called the lottery ticket hypothesis, which is a pretty snappy name, I think. But the lottery ticket hypothesis is essentially, it was driven by this desire to try and say from a theoretical perspective why we need such large models to begin with at training, if we can throw away a lot of parameters at the end without compromising test accuracy. And what they suggest, and I think this is very like an early direction of research, but they suggest that perhaps the lottery ticket hypothesis is that the model, there may be only a few winners, and there may be many sub-networks within a neural network, and that the lottery ticket is that you need to have the diversity of possibilities in order to end up with a winner. And I raise this not to suggest that this is an answer, I just raise this as an example of the type of fundamental research that's been inspired by this question. Yeah, sorry, question in the back.
Maybe it has something to do as well with those finding better chance of finding a global minimum, more room to move in.
Oh, excellent conjecture. I suggest, it really is, this paper was published, I believe, end of last year. I don't know, someone with Wi-Fi at the end will do a loop back of all the factors I put out there that could be incorrect. But it was definitely very recent, because this summer they were doing the final print-ready version, and it could, in fact, I think it deserves extra attention to understand how it relates to the loss landscape, which is another question we know very little about. Yeah. Go ahead. Sorry, you have like this inquisitive, yeah.
Yes. So, interesting question for someone who's working actively in this field. How much of the size of the networks, do you think is related to trying to relearn the same things at different scales and notations?
Oh, interesting. Huh. I'm not going to answer that question, but I'm going to perhaps, actually I'm not going to answer how size relates to it, because I actually don't know. I actually don't even know if you can address it hysterically. But there's an interesting blog post that was done, I mentioned it yesterday in the coding lab as well, not by Google, by fast.ai, and they were doing, essentially there's a whole set of benchmarks on the speed of training, how quickly you can train internet. And one thing they found was like they could, I believe it related to the size of the filters. So they changed the size of the filters over the course of training. And they did, I believe, again, I would love someone on the internet to fact check me, but I believe they did larger filters at the beginning and then switched to smaller filters. And that relates to how perhaps the hypothesis was when you're first classifying something, you want the big picture, you want to gain context, but then when you're trying to discriminate based on small differences, the small filters could be more useful. So that's not quite vague on what you're asking about the relationship with size, but again, it's this interesting idea of like, we almost assume that the hyperparameters we set at the beginning of training, we almost always as researchers just hold them fixed. And then we vary it between trainings to find the optimal hyperparameters. What they did I thought was quite novel, because they're essentially saying that there's different stages to the learning process, and let's adapt our, clear exceptions to this learning rate, like some others, of course. Yeah, as soon as I said it, I'm like, not quite. But yeah, but I do think like this is an interesting hyperparameter that they vary, because I haven't seen it done before. Yeah, is that all satisfactory?
Well, it's you can add to the. I was actually asking for you just your opinion.
Yeah.
So it doesn't have to be.
Doesn't have to be conclusive. Thank you for giving me that constraint. Excellent. So where are we? Again, my colleagues would call this subcategory of computer vision, which is object classification, rather than broader object detection, as fairly sold in terms of we have some methods that are very good out of the box at achieving a desirable level of accuracy. But I hope this talk has convinced you that that's one dimension of the problem. And in fact, like there's many other dimensions where not only is the subject of a curious amount of research, but it's a subject that there's answers like the one I just gave, which was like fairly incomplete, like, oh, I don't quite know if anyone's doing work on that, and that's very much open for attention of researchers. Oh yes, substantially harder. It is really substantially harder. I hope Danielle is able to touch on this in the panel. And there's other key challenges I haven't even talked about, which I think are incredibly important, like domain adaptation, which is really like, it's really this presumption that we are reflecting test set conditions when we use labeled data sets. And a lot of domain adaptation is, it's a fundamental component of generalization, because really what we want is we want the model that we eventually deploy to be able to still be accurate. And so what domain adaptation does is it tries to understand model performance given a different data distribution at deployment time. And so there's very structured data sets to measure this. But there's object detection, there's video generation, which is another fascinating problem, which has a time element to it. Oh, I even added this twice, just for video generation. Excellent. Go ahead.
Just to touch on the domain adaptation question as well. Like, I think at the beginning you said the accuracy of all those models as they get bigger and bigger improves, but isn't there the argument also that we've reached the point now where those models are almost overfitting to the training and test sets? That's why they're getting so big now. Now it's just essentially memorizing those like what billion image sets. So.
Yeah, this is an excellent reminder for me to mention the other empirical study that I wanted to make reference to, which is this, I believe it's called, it was by, well, one of the authors, oh, I hate it when this happens, when I remember the author that is considered most famous, but not the first author, that's awful. So I'm just not going to say any of the names, and you would guess. But essentially what they did was they had random noise as inputs. And they also did some, like, essentially shuffling of data. So it was incorrect labels to training. And the model is still able to perfectly arrive at a reasonable training accuracy. And so what that suggested is exactly what you're precisely contributing, which is this discussion that, of memorization, which is essentially, it's not quite clear what we're capturing with our test set accuracy. So summary, and then I'm super excited to go to the spotlight talks because they will, particularly I'm thinking in context of some of the questions and the comment from the gentleman of the capsules talk will be fun. I've already kind of talked about a lot of these things. I don't want to repeat things out loud. But one thing I will say is that Daniela raised a really important point. So she was saying, oh, you frame this in terms of applied problems. I think in looking at the last slide, I haven't really articulated this in terms of applied problems, mainly because I don't think researchers should shy away from thinking about how that work impacts the larger world. And because the breakthroughs have been so compelling in terms of what impact they can actually have, it's really spectacular to think of if there was actually the ability to deploy these models in many different contexts like healthcare or intermediate internet access or smartphones, how much we could achieve in advancing like various societal goals. So I don't think we should shy away from that, while acknowledging that it also is a core fundamental building block of why these models actually work. So I actually think I'm going to perhaps take 2 questions, but I want to make sure that we have lots of time for. Oh, you're taking a picture of my teddy bear. Oh, I'll put it email. Okay. that makes more sense. Okay, go ahead. Sorry, sir.
What exactly is the definition of a solved problem? I mean, I came across the term recently for the first time, and it was in relation to something that I personally think is definitely not solved.
Yeah.
And it seems like an incredibly vain thing to say. We've solved it.
You have pointed out something very lovely. I'm going to do a quick rant about this. Like, papers also say this. You'll see in a paper, they'll be like, it should be obvious for the reader to see. And it's just infuriating. Please never do this in your research. Firstly, it's a cheap way of communicating. So I'm thinking, so people do say this is solved, and they often say it like bantering over the coffee table, like, oh, the same way people love to say, oh, AI is plateauing, like without, but it's grumpy talk, but there is a sense that relative to the other demands of computer vision, it's more clear the gains that there's been breakthroughs, and perhaps I'll phrase it that way. Because I think if you talk about the subject of a lot of PhDs in computer vision now, they're trying to do things that it's much less clear whether a breakthrough is even possible. Go ahead. Then I would actually love your opinion on this. Yeah.
Just to add to that, I think it's really just a function of the metric which we define, which is, I mean, by nature, just human constructed. So I think that sort of really seals it for me. It's solved based on our evaluation of how well it's doing based on the metric that we set.
Go ahead.
Maybe to add to that
as well. Go for it. Yeah, I love this.
In a sense, if you look at some of the newer smartphones coming out with AI chips and those things, I see them that it's now commercially available in all the new stuff coming out, and including the cheap ones. And to that extent, I think that a lot of the image classification problems, you can start to say, well, maybe we have solved it well enough that it's cheap and it's easy and
it's been commercialized.
And it's been commercialized.
Yeah, interesting. That might be another dimension that it's had commercial success, perhaps. Yeah. A question for back. Excellent.
I'm curious to know what are the limitations of communication? Is it true that as long as you just have images, then solve the problem using computation?
Oh, so hopefully this is giving you somewhat of a taste there, which is that I don't think so. In fact, I think this. I echo Daniela's thought on this, which is that the whole goal of how we measure scientific progress is, according to, we have to have a way of measuring, and we create various dimensions, and then a community as a whole kind of jumps on one because there's a momentum to how we choose metrics, and so accuracy for a lot lot of computer vision history has been paramount. And accuracy is measured using, generally like in supervised learning problems, a labeled data set. But in fact, like I think you quickly get into off-road territory, perhaps that's the way of saying it, where metric accuracy isn't well correlated with clearly other important dimensions that we want to measure. You know, perhaps one of the most tangible is adversarial vulnerabilities. So maybe, so I'll do one question here, and then perhaps we should stop. I think we should stop. Daniela's nodding. Go ahead.
Would you recommend using a bootcamp from scratch or using a VJ?
Yes. So this question gets to so many good ideas, which is that we have cognets that, out of the box, have open source and have achieved a level of accuracy. What I will say is that this also speaks to an interesting gap between research and applied, which is that all these models have been developed given like 3 data sets. We all use the same data sets. We use ImageNet, Cypher 10, and MNIST, essentially to talk about how we measure progress. And often what I hear anecdotally from people who work on applied problems is that there are in fact like unexpected gaps between performance on these core data sets that the research community uses in applied. So I don't think that's an answer to your question. It's a statement more that it's very possible that you may take a state-of-the-art model and have to think a lot about how it works for your problem. But I would still suggest starting there, because at least then there's a consensus of what good performance is, and you know the model has achieved that performance. Whereas trying to design your own architecture from scratch, it gets into this very interesting territory of you're not quite sure if it's how you're doing it or if it's a data set. It's always good to have a baseline, which is well understood. Yeah, I'm going to stop, and I'm going to have Danielle introduce the Spotlight books, which are amazing. Thank you.
All right, my name is Daniel Adeshope. I am a student of Ladoke Archipelago University of Technology from Nigeria. So earlier this year, I went to see my auntie, an ophthalmologist. At the point in time, she left me and an old lady in the room. So this old lady has been diagnosed with an eye disease and required immediate surgery. So from where I was sitting, I could feel the pain this old lady was feeling. And that was one of the motivations that led to this project. Now the thing about retinal tissue damage is that it's more or less like a thief in the night. It's not detected early in it's not detected most times not in the early stage. So it is detected most times in the advanced stage. Hence, doctors that are specialists in this area called ophthalmologists are very, very rare. So and again, once vision is lost, there's currently no cure. So there's a need for a diagnostics tool that is accessible, affordable, as well as timely. So we just went online from the methodology that said lots of images from there, and methodology said lots of images from there, and we discovered that at early stage of diabetic retinopathy, the blood vessels they get weakened. And another thing, there's this tiny bulges in the blood vessels called microaneurysms. So we applied image processing on the retinal images and extracted the blood vessel area. We extracted the hemorrhage area, that's like small chunks of blood vessels on the retina, and also we also extracted this tiny microaneurysms. So these tiny dots there are the microaneurysms. So we applied image processing techniques to get converting the retinal images into numerical values. So we discovered that applying machine learning algorithms on these numerical values offered us good accuracy. And we saw that of the 3 features we extracted, the tiny bulges, which is microaneurysms, the hemorrhage area, and also the last one, we saw that microaneurysms are the most important feature in detecting macular edema disease as well as diabetic retinopathy. So this was more or less like a baseline. The image processing gave us a baseline for us, and it was working fine. But at the same time, this one was still there. We thought of what else would we come up with. So, but the thing is, getting retinal images normally can be very, very expensive. Yeah, now we call the standard procedure of getting a retinal image is using a slit lamp, and a slit lamp costs about $6,700. Now, of what benefit or of what advantage is an AI solution that is not affordable? So we decided to come up with build our own kind of full stack using a carton, using an empty plastic bottle, using a 20-day lens and a black sunglass. So the idea is place the custom fundus camera to the eye, get the image. This time around, I'm not using image processing techniques. We're using a deep neural networks. We took the retinal image, trained it using Inception V3 with TensorFlow and deployed on an Android app. So, but the thing is, why TensorFlow? We saw that TensorFlow was easy to use, scalable, production ready, compatibility with mobile devices, and works offline. No internet in less than 90 MB. So our validation accuracy was like about 80%, but at the same time, everything was not just good and sundry. We had some challenges too. Yeah, we saw that the pupil has to be well dilated before we could get the retinal image. We also saw that at the edge of our retinal images, there's this black semicircular shadow due to occlusion. We also saw that there's this, because the idea is to take the phone and place the phone at the back of our custom fundus camera. We saw that the flashlight from our phones were always reflecting on our image. So one of the ways we plan on working on that is get more training images using our custom fundus camera, take those training images, add them to our training set or our data set so that our test and our data set will come from the same distribution. We also thought of applying a lot of data augmentation techniques as well as image processing techniques that will expose the learning model to more variations of the retinal images. We believe that if we solve the problem of just one local community, then eventually we will solve the problem of the entire world. Thank you very much.
Hello everyone, I'm Ismail Kone from Ivory Coast, but now I'm studying in Morocco, where I do my PhD in machine learning and deep learning applied to medical image analysis. So in this presentation, I'm going to present a work on a specific disease, which is the breast cancer. So we know that according to the World Health Organization, each year many women die from breast cancer. So it's a threat for humans. And it's very important to take some proper action before the spread of cancerous tissues. So there is a way to acquire some images that are called history images that allow us to make a very early diagnosis and to take the proper medication. And you will see in the image, we are concerning in classifying this image in 4 categories: the normal, the benign, and the in situ carcinoma, and the invasive carcinoma. So both two are the cancerous. This is a low level. Here is a high level of cancerous. And to tackle this problem, instead of building a model that we classify all those images in 4 categories, we try to solve simple problem. First, we classify those images into 2 categories, the cancerous one and non-cancerous one. And then, other models, we classify each subcategories in the specific categories. So, the benign categories, the model that is, excuse me, so each node in this tree is going to classify incoming image to first the non-carcinoma image and the carcinoma image. And each node is in fact a model, a classifier. So for this classifier, we choose the ResNext, which is a well-known model, and which is the architecture. And we add up some set of layers in order to transfer them from the ImageNet model that classifies image into 1,000 categories for classify them in 2 categories. And we use a set of methods that are very interesting to optimize the training process. First, a guy from US Naval showed a method to choose an optimal learning rate. So we use the method to find the learning rate, and we use another method that is about setting different learning rates to different set of layers in the network. And the third method that we use is the stochastic gradient descent with ground start. And when we apply this method, so we use our method in the competition that has been organized this year, which is named Batch. It's a kind of Kaggle competition, but it's specific to medical images. And when they released the trained images, it was 400 images, and in my work, I divide the image in the trained image and the validation images. And this is the result that I got. It was very good. But when they release the test image and I apply my method on the test image, I got a result that was lower, much lower than what I get on the validation set. But I get, fortunately, the 8th place on the challenges, and you can see that many countries around the world compete in this competition. But here is some analysis that we were thinking about what might not have worked well. So, for example, I resized too much the images, and I didn't use at all the validation set when I trained my final model. And I made another analysis, which is the specificity and the sensitivity of my method. And it was very worse, because on the main one, I got the best specificity, but at the same time, I get the worst sensitivity. So my method was very worse at classifying images as being. So to conclude, this idea of tracing this image like a tree decision works well, but there are many things you have to improve. First of all, the first remark, according to the speech of Sarah, she talked about the interpretation. So now is the time for me to look at the feature that are used to classify those images and to spot the problem why that is not able to classify correctly the main one. And then try to use all the image, the validation set to train the final model. And so when we reduce the image, so I make some crop of image, so it's a bit better to not crop the whole image and use the parts that are missing. So these are the perspective. And so I thank you for your attention.
Good morning, everyone. My name is Benjamin Akera from Makerere University, and I'll be presenting part of my undergraduate research work and experiments. This is work done at the Makerere University AI Research Lab. So the Makerere University Lab has a project that involves giving phones to farmers, and they keep crowdsourcing for us data of images of cassava leaves. But some of these images are dirty, and we require good quality images to perform classification of cassava diseases. And it's important for us to build models that use clean images. So the data set looks like this. It's five classes of diseases. And these are bacterial blight, mosaic, and healthy. So what we want are images that are clean and that show us what the contents of a leaf are. So we can see here we have very clear images, and this is what we expect to get. But then what we get from farmers are something like this, images that have so much background clutter and noise. And the idea was to use an approach called semantic segmentation to help us ensure that the data we're getting from the farmers is actually clean before we can use them for classification of diseases. And so semantic segmentation is simply classification at pixel level. So considering an image like this, we want to know what pixels belong to what classes, okay? And our goal was just to improve the accuracy of the in-field diagnosis models that the AI Research Lab had already tried to deploy. And our methodology included collecting data from both from the field and from the data set that had already been collected by the lab, training a segmentation network that was called INET, and then working on using the clean images to and passing them on to a classifier and then deploying this either on the server or on an Android mobile device. So annotation involved trying to label the pixels on the focal leaf so that we could train a segmentation network to know what pixels belong to the leaf and what belongs to the background. And we used INET, which is an architecture for real-time semantic segmentation, and it's capable of running on mobile and embedded devices. The core components of INET are similar to the Inception module in the Inception V3 network by Google, and we also have these bottleneck features that combine convolutional layers, regularization in parallel, with max pooling and padding. The core architecture of INET follows an encoder-decoder architecture with an encoder that maps the input data to lower dimensional spaces, and then the decoder that tries to bring the image back to this original data space, and then these keep connections in between so that we can have the decoder recover the object details better. So we trained this on about 1,000 images, split with 700 training and 300 testing. And we did this for those epochs, and we achieved 80% validation accuracy on the test set. And to reduce overfitting, because we had a small data set, we tried to use data augmentation techniques like superimposing a leaf on so that it can look like, so this is like a way of synthesizing data. And then, so these are the results we got from our preliminary experiments. We had ways where parts where the model could perform near perfect segmentation to remove the background noise, and those that performed poorly, like this. So from comparing the two models, we can have a threshold above which we can understand that this is a good image, and then below which we can know that this is a poor image with a lot of noise. So the conclusion is that if we have a raw image and we segment it to remove the noise, we can have these good quality images passed on to a classifier that can be more robust to noise and better. So semantic segmentation provides a way of ensuring good quality data is collected, and we plan to explore more robust segmentation models like Mascara CNN, and we have done some work on deploying these on mobile devices. Thank you.
Hello everyone, my name is Ahmed Mansour from the University of Khartoum, Sudan. I'm undergrad. So I will be presenting my work on using on a deep learning approach to tackle the problem of automatic traffic accident detection. So I started the problem statement. The problem we're trying to solve is to design a system that is capable of automatically detecting and reporting traffic accidents in real time from live traffic surveillance videos. So in simple words, what our system does is accept a live traffic video stream as an input, analyze it, and produces an alarm whenever an accident happens. So it's a reactive system, not a predictive one. So what motivates us to do this work is that traffic accidents can cause serious injuries, as you know, and every rescue minute, every response minute from the authority can mean the difference between life and death. Also, traffic monitoring centers that are responsible for traffic monitors rely on human observations. Those human operators sit in front of multiple screens, and there is a high chance of missing an accident as it happens. So an automation of this problem is required. So regarding that said, there is no publicly available dataset specifically oriented to this problem, so we constructed our own dataset. Most of the videos were collected from two main sources. Most of them were collected from Sudan General Administration for Traffic Control, and some of them were collected from YouTube. The dataset consists of 79 videos. We ensure that there is different accident scenarios, different illumination conditions day and night, and so we use data augmentations, all of this to ensure the diversity of the dataset. These are some samples from the dataset. Some statistics. The dataset consists of about 18,000 frames divided into train and test sets. This is a map showing different locations where the videos were recorded, mostly at Khartoum area. So that we have defined the problem and described the dataset. I will describe the approach we take. So we first use transfer learning to train a VDD16 component on our dataset and group every 20 video frames together, pass them through the VDD component to extract the spatial feature. We took the output of the last pooling layer, stack them together as a long sequence, and then fed them to an LSTM. The purpose of the LSTM is to capture the relation between the frames, all the interframe dependencies. Then a fully connected layer for classification into normal on an accident. In case of an accident, an alert will be fired. This is a demo. Okay, I'll present it then. This is the result, the training and validation accuracy, and this is the loss, no sign of overfitting as you see. This is the F1 score in the test data set, and this concludes my work. Thank you.
Hello. So, hello everyone, and thank you for your attention. My name is Jean-Michel Amassa, and I am currently working as a machine learning engineer at the Research and Development Institute in Dakar, Senegal. So basically, I am working with submarine acoustic data, and as you can see on the right, this is the path that our oceanographic vessel took to record those data. And the principle is very simple. As you can see in the central picture, at a regular interval of time, the vessel sends into the water pulses of acoustic waves. And when those waves meet solid objects, they are reflected back to the source. So it is the principle of the sonar. And we can make inferences about the nature of those objects. And so basically, I'm interested about the nature of the seafloor. You see the bottom. And we can have solid bottom, and in those cases, the data, the reflection will be very clear and very easy to read. So that's what you can see in the upper picture. And sometimes we can have a softer texture, or we can have high density of fish lying on the seabed. And in those cases, the reflection will be a lot harder to interpret. And basically, today, basic procedure can't detect where the bottom is. So we rely on the work of human experts to label those data. By the way, those kinds of data are called echograms. And at each column of the echogram, is called a ping. And as you can imagine, a whole data set is very big. It consists of millions of pings. So it is quite tedious for someone to do it. So my work actually is basically to train a learning algorithm, basically neural networks, to do this procedure, to classify the echogram into two categories. One where the bottom is clear, and the other one where the bottom is unclear. And the end goal of this is to have a system so that you can fill in the data, the echogram, and output those two categories so that we can give to the expert just the unclear echogram, so that he can just focus on this, and it will make his work easier. So thank you very much, and if you have any question, feel free to ask.
Hello everyone, my name is Dion. I work as a design engineer at Innovatics Consulting, where we use computer vision to address our clients' needs. Now, aerial surveys, or counting elephants from the air, are a great way for ecologists to determine the overall health of a population of elephants. We at Innovatics believe that the current method of doing so, using human observers in aircraft, can be improved upon by making use of automation and the recent advances in deep learning computer vision. To test this idea, we took a Bushcat Light Force aircraft, cut a hole in the bottom, and stuck in 3 cameras. So the pilot then flies over the region where we want to do the survey, collecting images. When the pilot has landed, we download these images to a processing computer. Here, we want to go from images like this to ones like these, where the location of elephants are highlighted so that you can automatically count them. To do that, we took your typical ImageNet trained convolutional neural network, adapted it to our problem, and retrained it using some images we collected over the run of the project. We end up with a network that can be applied to an image and that highlights the likely location of elephants. So over here you can see that in the green box an elephant has been detected, in the blue box the 2 elephants, and the red box we've also detected a tree stump as an elephant. Now that's the problem. Even if you have a very good classifier that is performing very well, you'll still get a high number of false alarms just because of the size of the images and the number of them that we're collecting over a survey. To address this, we've built a verification tool that allows multiple users to quickly run through all of the detections and then reject or accept those that are accurate. So our solution isn't completely human labor free, but it does reduce the amount of man hours that you need to complete the survey quite significantly. To test our idea, we recently completed a comparison exercise versus a human survey group that were very experienced in Botswana. Using their observations as ground truth, we were able to get an error rate of approximately 3%. Due to the experimental setup, we were not able to determine how many elephants that they had missed. Now also, when you take into account that we're flying a lot higher than the normal survey group, and we're detecting elephants that are outside of their search trip width, if you take this higher population count and you normalize it for the greater area that we search, we end up with a final population estimate that is pretty much equal. Actually, it's slightly higher, but it's equivalent to what the human survey group got. During the run of this project, the biggest problem for us was just getting the data, because there aren't really a lot of data sets out there that contain images of elephants in the air. It took a lot of hard work, lots of manual labor, and then we also used a lot of data augmentation and hard negative mining. So to conclude, we're quite happy with the progress we've made with this project, and we're looking forward to taking what we've learned with this project and applying it to other conservation efforts that we're running at Innovators Consulting. Thank you very much.
All right, let's give all our spotlight speakers So are there any questions for our spotlight speakers? So feel free to direct any question at any one of them. Yes?
Me?
Yeah?
Yes, I had a question about the max pooling, right?
So who are you directing your
I think the IBM piece of it. And I guess anyone in the room as well. So the example that you used to show an issue with max pooling seems to make sense, and it's quite intuitive. But what I realize is that when we do max pooling, we're working with 4 pixels at a time in the 2x2 grid. And we generally won't have those kind of objects like an eye within those 4 pixels. So does it really matter if we're looking at things, or if we're doing max pooling at such a local level? Is my question.
Cool. So max pooling, like you kind of said, we're doing in a 2x2 grid over there. But if you can imagine that we're stacking a whole bunch of these layers on top of each other, so you could go from a 2x2, but by the time you've stacked a whole bunch of max poolings, your receptive field is a lot bigger than that. So you lose the ability to tell the spatial differences between objects at a much bigger scale than just, I mean, if you only use one layer of max pooling, maybe you wouldn't have such a problem, but you stack them up and lose many. That property of max pooling can be desirable, and is desirable, in that it gives you what they call invariance. So if something moves a little bit from left to right or up and down, you can still say, okay, that's a face, you're not perturbed by it. But it does cause some other issues.
Any other questions? Yep, that's it. Yep, you ready?
Yeah, so she's asking about the class imbalance. So because we're considering the whole of the image, and we only had a very, initially we only had a very small sample of elephants taken from the area. So to address that, we did a lot of data augmentation. So that's basically taking the samples that you have and rotating them and swapping the views and modifying the contrast levels so that it appears as if you have a lot more samples than you actually do. Then also what we did is we used hard negative mining so that we run a network and then it would find some of the elephants and then it would identify some spots within the image as elephants themselves, which are incorrect. It's like a rock or an anthill or whatever. So what we would then do is we use those samples specifically and put them in our negative class, our background class, and that would then improve the performance.
Yes. Oh, yeah.
On the issue of counting the elephants, because they're moving objects, how do you make sure that you reduce that approximation error?
Yes. So yes, she has a very good point. Elephants are moving. So what we do is in our system we're taking overlapping pictures. So there's like a photo every 2 seconds, and then you have a bit of overlap between the pictures. So as part of the verification process, we also do registration, where we have to identify elephants that we've detected multiple times, and then we mark them as such. And we have some tools that do that for you automatically, and then that will help you to prevent double counting.
What those tools that you talk about, how do they do it?
Okay, so what we do is we make use of Huggin, which is it's a suite of software that does panorama. It builds up panoramas of images, and to make panoramas, you need to get the transform between the images, so that it states to you what the transformation is between each image. So if you have that, then you can project the position of an elephant in different images. And if you can get that, you get a good idea of where you expect an elephant to be in your overlapping images. And then we built another tool, like a verification tool, that allows you to mark them and automatically match them.
Okay, two last questions. All right.
Eventually, we find out that there are enough relevance at all.
Yes. In the end, so we were quite lucky enough that we got to fly a couple of data collection surveys in Botswana, where there are quite a lot of elephants. And from getting all those samples that we got and through the data augmentation, we eventually got to a point where we can say, okay, we have enough elephants now. We'd always like more.
All right, so the lady behind.
My question is actually for the first speaker.
Yep. Daniel?
So Daniel, I know that you did similar research that was done by Google AI.
Right.
So how is your research different from what they did? Because they also used deep learning for detection of return on return.
Alright, so we actually started with image processing, and that was like our baseline. Yeah. One of the reasons why we went further was because the approach we were trying to look for was we wanted to try something that was low cost. And that was what led first to trying to build a custom for this camera. So now, I haven't checked out what you just said, but we saw that using our focus camera, we could get images with them, add them to the training set, and just go further. So it's just like something that is still in idea stage, something we're still working on. It's not yet perfect yet.
Cool. So let's frantic hands all over, so you can take a lot of these questions offline, just so we get a little bit of time for the panel. Okay. So if I can now ask all our panel speakers to come to the front.
I'm back at the front, but I'm going to try and pass on on the pressure as soon as possible to our wonderful panelists. So we don't, because of how amazing the spotlight talks are, we have bumped a little bit of time into the panels. I'm going to dig right in and presume that we are no need for the polite forays, but I want to kick off the point of this panel, and like especially, I'm quite low. This is okay. Oh, okay, I'll do that. Well, maybe you have advantage, and I'll feel intimidated asking the questions, looking up. So what we're trying to do with this panel, and I sense chatting with all of you, is try and get a sense of what are the questions that researchers are working on, and what is exciting to each of you in your respective domains. And I think to start off, I would love to ask each of you to talk about a problem that you've been excited about. Perhaps it's something you're currently working on, or perhaps it's something that you're working on in the past. And we can start with Richard. And Richard, it was funny, I was looking at your papers, and I thought it was like an intriguing moment for us to segue into this panel, because one of your papers about how to tell people to pay attention in a classroom, and I thought it would be a good application for this moment in this parallel track. But Richard, you're also a lecturer and in machine learning at WIT, so perhaps I'll start with you. Like, what have you been excited to work on?
So for me, I quite like to tie the research to the teaching. And so most of the stuff that I do is looking to try and say, how can we improve teaching in some way? And being at a university, the obvious thing is, how do you handle big classes? And so when you talk to a group of 10, 15 people, you know who's paying attention, you know who cares and who's falling asleep. But if you have 300 or 400 people in a room, unfortunately the answer is usually all of them falling asleep. But when you've got a big group like that, it becomes a lot harder to keep track of everyone and to really understand what's happening. And so often what lecturers do is they just kind of pick a sample, and you look at those people and those people and those people and kind of hope that they represent everyone. And so the idea is, can we build a larger system that monitors people during lectures and looks to see who's paying attention, who's engaged, and then eventually, hopefully, to be able to say, well, why are they disengaging, and what can you do to re-engage them?
There's an interesting follow-up there, and I think researchers in the community, we think about this a lot, but we have a particular task that we craft a solution for, but there's also perhaps the concern that that solution could be used in unintended ways. Like, how do you navigate that also as a professor teaching machine learning to your students? And by, I guess, unintended ways, I guess my suggestion is that if you're using machine learning to monitor, there's perhaps degrees of freedom there.
Yeah, no, absolutely. I think you have to be very careful about the interpretation that you get from systems. So I think there may be two levels. So the one level is to say, well, should students in that aren't paying attention be penalized or disciplined in some way? And I mean, is that really something you want to be doing? And I would argue that that's probably not something to do. And I think you need to be very careful with stuff like that, where you say, just because someone's not paying attention or because they're disengaged from something, you don't, it doesn't necessarily mean they don't understand. In fact, often if they're not paying attention, it might be because they understand, because they already understand. And so I think you need to be very careful with those things, and a system in general, and I think a lot of the machine learning things that we talk about, in many cases we're talking about correlations, and we're not necessarily looking at causation. And so, for example, for a system like mine, you wouldn't want to say that students that are disengaged mean that the lecturer is bad. And you would need to be very careful about educating people who are using the software and also the policymakers who decide how to use these kind of systems. Where you've got to make sure that it's very clear what the systems can and can't do and what they're actually telling you. And so for me, the system is basically to say, this is the current state of the class, how can you do better to re-engage them? How can you fix a current problem as opposed to identifying why a problem happened.
We might just hold, oh, this is so exciting, I can tell. I just want to make sure that I kind of introduce some of the themes that I want us to all talk about. I love that you said that. I think that's very interesting. A lot of the simplification in terms of how machine learning is discussed in the media is this idea that perhaps like the shocker headlines of like AI has learned its own language, or perhaps precisely what you're describing, this idea of correlation versus causation. So I want to, Daniela, I would love to hear your answer to this question. I think your background is fascinating because you're doing a PhD right now, but also the topics that you're interested in working on are this idea of like working across different modalities and also human-computer interfaces, which a lot of perhaps the research that I've been doing actually abstracts away. And so I'm fascinated to hear about both what excites you as a problem and also the challenges that someone not working in that area perhaps wouldn't anticipate.
In this audience, so that I have the freedom to gesticulate wildly.
Oh wow, so much more graceful. So yeah, I've been working in combinations of computer vision and natural language processing, and specifically looking at the ways in which this can be combined for things like visual question answering. So visual question answering is given an image and a question, can the system predict the answer to this question? And generally the question is grounded in the image. Okay, so it requires both an understanding of the image, understanding of the language itself, and then the answer is hopefully correct. And what we see with a lot of these systems is that the way in which the image is being represented is pretty simplistic. So we saw in Sarah's talk that these images are sort of shrunk down to image feature vectors, so in the case of like classification, and that is the sort of feature vector or image feature vector that is then used to predict the answer. But when you think about like what answering a question about an image actually is, it requires often a much higher order understanding of like the concepts and the objects in the image. And I think that's what excites me at the moment about the sort of direction of computer vision. What we've seen so far is just very much like an object-centric focus, where we're just looking at very simple things, like we're just sort of treating an image as a collection of objects. And we're sort of looking at it in different ways. We're saying, okay, we'll classify the image, which is where you just detect the main object, detect the objects, so just localize where they are, or like slightly advanced image segmentation, where you're saying, okay, these pixels belong to these objects in the image. But if you sort of go beyond that, we should start to think about computer vision as visual reasoning in a sense. And that's what really excites me going forward, is how we can extend computer vision pipelines to incorporate things like the relationships between objects, their functions. And I think this is really important when it comes to, for example, answering questions about images, or in like maybe a self-driving car, like knowing, or even interpretability, in fact, in your work, like being able to reason about those higher order concepts. So yeah.
Yeah, that was excellent. I'll try and read this more gracefully, perhaps, as well as Daniela did. That was, you got it, really this idea of just extracting conceptual understanding from the way that we consider representation of information in images, which is really important. Natalie, your background is both just a very interesting, rich set of work on computer vision, but I love that you actually touch on something that I've thought a lot, which is this idea of aesthetics, or this idea of just human-centered metrics of success. And this was something that came out in the talk my talk, Daniela asked a question, which kind of got at this. It said, we evaluate progress in a task according to a very human-centered notion. I would love to touch on that, but perhaps I jumped ahead a little, so perhaps you could introduce what I kind of hinted at there, and then some thoughts on that particular problem.
I'm just going to hold it up.
Yeah, so I am quite interested in work in computer vision that looks at what we call subjective properties of vision. So basically aspects of vision that's going to vary from person to person. You know, very often in many machine learning tasks, it's a very nice paradigm to be able to say, you know, you have your data set, you have a supervised learning problem, you find, you know, you have a supervision that's fairly objective, like, is there a dog in this image? Is this a landscape scene? Things like this where you find pretty high agreement between different observers, right? A different problem are things like aesthetics or things like even visual attention, where you're going to have a range of experience. It's subjective, there's no actual right answer. It's not, you know, if someone says, I find this image beautiful, you can't tell them you're wrong, right? So I've done a fair bit of work on this problem and trying to understand, given that there is this subjectivity, what can we do that's interesting in this space? Should we just simply say, well, this is not something that machine learning can tackle or computer vision can tackle? Or what kind of interesting questions can we answer given this subjectivity? So I've done a fair bit of work, like specifically on the aesthetic space, in trying to at least have a sense of the variability of opinion, for example, about aesthetics. So saying, because for example, there's a lot of communities online where people go for help and for sort of guidance in terms of, for example, pictures that they might take. There are quite a lot of online communities that do this. So, and it is quite a very interesting and very rich community to kind of interact with. So one of them is called DB Challenge. And this is a place where people go, and actually they're like weekly challenges where you know, you sort of challenge the photographer to develop a skill or to have some type of photo. So one example might be take a bokeh photo. So if you don't know bokeh is like this sort of aesthetic style where there's sort of like this, I don't even know how to describe it. It's you kind of get these artifacts that look like there's some sort of a close-up in certain parts of the image, and then some parts of the image is more blurry. It's very beautiful. I wish I could show you an example. But it's a very beautiful and very well-known photography style that if any of you would recognize it, even if you didn't know the name of it. But it's very challenging. And so basically it challenges the users to take photos in this style, and then afterwards you get a lot of very constructive critiques. So for example, there's like a web forum, someone puts their photo up, and then a lot of people give you constructive criticisms. Like for example, I really like the color, the contrast that you have, maybe the composition could be a bit better, and things like this. So some of the work I've worked on are on things like being able to produce similar criticisms, being able to produce similar score profiles to say, for example, given this photo, the average user would say that your photo rates a 5.5, or many people might like it, but there's that minority that won't like it. Or, for example, how would you tag this image? So what kind of style would somebody say this image has? So basically, the approach I took was a very data-driven one, saying that given that we know what a lot of humans have said about this photo, how could we sort of reproduce this feedback that, you know, like a community of constructive criticizers basically would tell you.
I think perhaps I'll just start awkwardly shouting across, so then you can repeat the question I asked, so we have more like rapid flow. But that's, I mean, what you touched on is really fascinating. This idea of measuring progress, and like this idea of measuring progress given a divergent ground truth, perhaps. There's perhaps I'll frame this as a question, but there appears to be recent work that suggests that by trying to kind of bake this into a labeled data set of some kind, you can almost automate the task of finding aesthetically pleasing images. I'm curious, like, whether you think that essentially delegating the task of finding the most aesthetically pleasing image, or the one that's correctly optimized for a person, is a reasonable approach. By that I mean, should we just delegate problems like this to a model? And perhaps I'll, just to save myself doing the mic back and forth, I have a wider question as well that you can pick and choose how you want to answer for the panel as a whole, which is that Given that your current areas of research, what do you think is one thing that is perhaps holding it back? And so, yeah, maybe we can kick off for Nyla again, straight back to Ben.
Sure, so as to your first question about is it reasonable for us to sort of pass off this type of feedback, let's say, onto a model? So, I mean, it's complex. So a lot of the stuff I've worked on is really on giving you, let's say, average feedback, right? So, I mean, the types of approaches I've taken is statistical machine learning. So in the end, you're working a lot with averages, and it's not always easy to get a range of opinion, and so that might not always work for everyone. So that's a definite challenge. So one thing about aesthetics is that we've talked a lot about the fact, I mean, I've just described the fact that it's a very subjective thing. So there's not going to be one opinion. So that's certainly a challenge. I do think that there's a usefulness in having, let's say, like a summarization of opinion. But I wouldn't say that it's the end of the story. And there's actually a fair amount of interesting work going on optimizing for specific styles, for example. So saying for specific people. So there's a lot of work, for example, on style transfer. And style transfer right now is, you know, if you have like a specific artist that you're interested in, or going even more broadly, if you have a specific style, right? So I'm trying to think of a style that goes beyond like one artist, but you can think of some of them. And that at least goes a bit of a way towards personalization. So rather than saying, you know, your image rate's a 5.5, and you can, for example, think of feedback like, I think you're going for this style. Maybe if you wanted to go for this style, you can sort of tweak your image this way. And that way you can go to something that's a bit more personalized and a bit beyond just sort of giving you a score that might be not that interpretable. And so maybe moving on to your next question about things that are holding computer vision back. So, yeah. I mean, I think there's, you know, it's hard to say. I mean, I don't think there's anything that's holding computer vision back, at least not that I can think of, that's very specific to computer vision. I have a bit of a biased point of view because I really look at computer vision from, at least in my later research, I've really taken a very data-driven approach. So a lot of the problems I think of with computer vision are actually just machine learning problems that you can kind of extrapolate to almost anything that uses a data-driven approach. So I would, you know, I would mention all the things, right? Domain adaptation, that's it's a huge challenge and also opportunity, and it's something that I think is a very interesting thing that there's actually a fair bit of research on, and I think there's been kind of a renaissance in domain adaptation right now. You know, I was in CVPR this year, so CVPR, as you probably know, is the biggest, I guess it's the most well-attended computer vision conference every year. And it was amazing to see how domain adaptation was just everywhere. And for those of you who were there, probably noticed it too. And this is something that we worked on quite a bit in my institute. For many years back, way before the deep learning days, now I think people think of domain adaptation, all they think about is just weight transfer. But there's been so much stuff done in different paradigms with this, and I'm starting to see the work coming back, which is also, I think, a nice lesson of deep learning in general and machine learning, the fact that people always think that you need to throw away everything that's been done before deep learning. And it's really just, you know, there's this first wave, and then you start to realize, actually all the tricks that you learned before that people thought were not necessary for deep learning, oh, now we have deep learning, we no longer have to engineer anything. And it's sort of like, actually we're doing like exactly the same thing. So that's interesting, because then you can really look back, and I really encourage all of you, whenever you have a problem, don't think you can only look in the papers in the past 5 years. Like, you will find things that are completely relevant that were published 20 years ago, and you see this all the time. I mean, even in deep learning, so many works, there's always somebody, right? Somebody says, oh, I have this new method for training a deep network, and somebody raises their hand, I'm sorry, I did this 30 years ago. But it's actually true very often. So it's very nice to sort of look back at works that to really do a very thorough literature review, because you'd be amazed at the things you find that are quite relevant.
Just to add a point actually onto the domain adaptation topic, I think that it's a particularly interesting problem in an African context actually, because a lot of the data sets that we see have this very westward bias actually, and you know, we sort of see these environments and photographs of people that you know, are just, they're very biased in that sense. And so domain adaptation and looking to see, using the data that we have and then sort of transferring that knowledge to contexts and areas within Africa that are interesting and important for us, I think that raises a very interesting part of domain adaptation. And then just to go back to the original question about sort of what do I think is holding us back. Within the computer vision community specifically, I find that there's a very sort of metric-driven, it's very metric-driven, which differs from, I think, other areas of machine learning. So, such as, well, for example, just looking at, for example, NIPS as a conference venue, I think it is more accepting of a paper that is something novel or interesting in methodology, whereas in the computer vision community, it's like, oh, your model didn't beat the state of the art, and this is therefore not going to be accepted into the conference proceedings. And I think that's something that's quite specific to computer vision, and I think that holds us back, you know, because it's rather than exploring, you know, new ways of doing things, new thinking, it's sort of, well, send the PhD students to take this neural network architecture and just squeeze it as much as possible until you can tweak and tune and beat that, you know, state of the art by, you know, 0.1% or 0.5%. So I think that's something that holds the computer vision community back.
I want to tweak the question a little, so you can still answer that one. Feel free if you go for it. But I also want to tweak the question for both of you because you're currently doing your PhD and you're teaching, and now that you're not currently teaching, but you've taught in the past and you've been actively part of.
I've been a teaching assistant in the past doing my PhD.
Yeah, excellent. But particularly because you're currently in an education setting, I'm curious. What do you think the biggest obstacle is for people who are just coming to this field in terms of grappling with how to contribute a successful idea? And as that, yeah, so I'll let you pick and choose.
So in terms of, I think, one of the big things for people coming in, and maybe this isn't necessarily a computer vision thing specifically, but more general to machine learning that we're seeing. And interestingly, it was something we were discussing as a committee the other evening, where the quality of the work and stuff that's happened here and the quality of the people here is high. There's a lot of very smart people doing a lot of good work. And I think in a lot of cases, a problem that we have in Africa in general, I think, is an issue of confidence. That the people here are as capable of doing these things, and so many times, because of where we are and kind of where we come from, we undersell what good work is being done, and that actually there is a substantial body of good work that's coming, and yeah, people are doing some good stuff here, and then must push and do it. And then likewise for new entrants coming into the field, I think it matches as well that we don't need to sit back and say, sure, the stuff that's happening over there is incredible, and I mean it is incredible, but it's doable, and the people here can do it, and it's just a case of jumping in and really saying we can do it and start doing it.
I thought maybe I can give sort of two pieces of advice, being a current PhD student, to those who may be starting. And I think so the first is it's really important. So now we have these fabulous deep learning libraries, TensorFlow, Keras, PyTorch. And they're really awesome because you can sort of plug and play all these things together and get something up and running relatively easily. And I think it's really important for those entering the field, especially within this what they call deep learning era, to actually, you know, it's not just a sort of let's plug these things together and do it. I really would recommend sort of going into the code, as I think Mustafa said earlier this week. You have to implement it at least once from scratch yourself. And so I think that's really important. So that's sort of the first piece of advice that I'd give. And then the second, and I've only really come to this realization quite late in my PhD, but you need to be the masters of your own learning. So as a PhD student, I arrived thinking, okay, well, I've got my supervisor, I've got postdocs in my lab, who are going to, advise me and guide me on what I need to do. But I think, you really need to be the driver of what it is that you want to know and what it is you learn, and that curiosity that you're just sort of following down this rabbit hole of what you find interesting. So I think those are my two pieces of advice for anyone beginning graduate study. And there are ups and downs, so even in the downs, don't forget the ups.
That was really, I really like both of your commentary, actually, because it kind of gets to both the perceived gap between you're discussing in terms of between the academic communities elsewhere, and I do agree it's perceived, and then what you're getting at is just really what the idea of typical fundamentals, that we have so many tools, but this is echoing what Naila was saying as well by the work in waves. I think a large part of the realization is just understanding that many of the best researchers is just simplifying the scientific method and essentially focusing on the methodology, and also taking account of what's already being done. I wanted to ask you a question, and then I would love to open it up, because I think that I saw a flurry of hands. The question that I have is, earlier, the theme of this panel is frontiers, and earlier we discussed perhaps one turning point in computer vision, which was the success of convolutional neural networks in 2012. But I'm curious to hear, especially given the fact that you're doing research, what are other reference points where you actually thought these were meaningful contributions that offered a different perspective to the field, or that you thought were particularly compelling works? And if you can think about why, even if it wasn't successful, according to, we talked about metrics, and I think the point was raised several times that metrics are quite subjective. Given any dimension of success, why do you think it was interesting? I don't know who wants to start. Maybe I'll pass it to the end and we can come back.
So, I can just point to one that just popped, the first one that pops into my mind, but it's certainly not necessarily it's not in some sort of order of ranking or anything like this. But I do think that, and I think it's a nice lesson in sort of multidisciplinarity. The whole field of the whole visual world revolution was another very important revolution. So how many of you are familiar with the concept of visual words, bag of words? By a show of hands. Yeah. So most of you, or maybe half of you, but this was basically bog standard. This was the standard approach to statistical machine learning for images for, let's say, maybe 10 years, right? From, let's say, maybe 2003 to 2012, this maybe even a bit further. And I thought it was very cool because this was a concept, bags of words, that really is, as the phrase suggests, right, that came from the NLP community. And it was a very nice adaptation of a concept to vision. And I think that there's a lot of interplays between different sort of AI fields, machine learning, of course, in general, NLP, speech, audio, that can really revolutionize another field. So, for example, this was NLP was bags of words were very standard in that area, but because words are these sort of discrete things that are very easily, represented as vectors, like binary vectors, you have to make a bit of a leap to try to put it into the visual domain, where you might think that things are more continuous, and how do I make this concept transfer to this different scenario? But when you make that leap, it can really change things. And so, for example, thinking of an image so before, there were a lot of what we call global representation. So you have an image, and you find some vector that represents it well. And then going from that into thinking, no, there's a lot of local structure, and how do we capture images as bags of sort of things of local structure? And that was really the concept. And that actually changed things quite a bit. It led to a huge boost, like another boost. I mean, it basically, because of that, you had the problem of even image classification come up. Before, like 2003, 2004, people were very focused on geometry, and this concept of really being able to tag images using things like kernel vector machines and things like this really started to actually work and become something that people felt was actually feasible. So that I thought was very interesting. Number one, because it was a real leap, and it sort of opened up this whole field of how can we do a lot of supervised learning in computer vision, and then also because it really was a nice way to sort of build gaps and build bridges between different fields. Another example of that is actually a lot of work on generative models. So for example, there's a lot of work on speech in terms of having these universal models for speakers and for speech. And a typical way of representing speech and generative speech was using things like GMMs and HMMs. And then that became actually very popular for representing images once again. Because once you made that leap from bags of words, you started to make a leap to being able to use mixture models, where your mixtures were mixtures of words. And so you can see that there's a lot of returns coming in just from making these connections.